Sound check 1. Okay, let's try and resume. I'm not sure what the problem is, but we'll see how it goes. We had left off with problem number 1, and the last part asked us to find the velocity when s equals 0. So we had set s equal to 0, and we got the equation 0 equals negative 16t squared plus 224t plus 16. Oh, that should have been plus 168, excuse me. There we go. All right, and then we divided both sides by negative 4. If you're able to follow along here on the screen, check my arithmetic, make sure I divided everything correctly. And then the next thing we need to do is to solve that quadratic equation. We could try to use factoring, or we could use the quadratic formula. Okay, if you're able to hear me, please respond in the chat bar. That would be really helpful. Okay, so I'm going to copy this equation over to another page and work it out. If I can grab it. I think it's going to let me. Oh, it worked. Okay, good. All right, so remember the quadratic formula is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. So that would mean that t could be, the opposite of b would be positive 56 plus or minus the square root of 56 squared, which would be 3136 minus 4 times negative 42 all over 2 times 4 is 8. So let's see what's under that radical there. It's going to be 3136 minus 4 times negative 42 is going to be 3808. So we have t equals 56 plus or minus the square root of 3808 all divided by 8. Is that a perfect square root? 3808. No. But we're using decimals anyway, so let's go ahead and approximate this. So 3808 square root is about 61.7. So we have 56 plus or minus 61.7. over 8. Okay, so then we're going to have 56 plus 61.7 divided by 8. Please, at home, if you could double check my arithmetic so that we know if I make any silly errors. 14.7. Okay, so we also get a negative value, but time isn't negative, so I think that we'll be safe just going with one value. And then let me see what they're looking for actually on this one. Yeah, just one value. Let me make sure. How are we doing so far? Let's see. Seven, yeah. 128. Okay, so far so good. Let's get back. All right. So now we need to find the question was, what's the velocity at that time? So we're going to have to plug into the velocity function. So we're finding v of 14.7. And remember, the velocity function was the derivative of the position function. So it was negative 32t, so negative 32 times 14.7 squared. No, not squared, because we took the derivative. And then plus 224. So negative 32 times 14.7 equals negative 470.4 plus 224 gives us negative 246. Negative 246.4. Now I notice on the answer key this is actually a 0.72, so apparently I didn't take my decimal place out far enough when I took the square root. By the way, if that happens to you on the test that you entered negative 246.4 and it marks it wrong and it's supposed to be negative 246.7 or something like that, please do take a minute to email me, and I can manually adjust your grade. I'm not worried about the point, the decimal places. I'm worried that you understand the basic concept. Okay, so that was the last part of that question. Question number 1 from the quiz to review for test 3. So our answers turned out to be 128, 7, 952, and about negative 246. Okay, so any questions about that one, or any preference on the question that I work next? And remember, you can open this document and look at it as we go by following the link to the OneNote file. It's posted in Canvas. It's also available in an email I sent out just prior to the live chat. Okay, if nobody has a preference regarding the question that I work next, I'm probably going to move on to number 3. Okay, so number 3 says a child flies a kite at a height of 50 feet, the wind carrying the kite horizontally away from the child at a rate of 26 feet per second. How fast must the child let out the string when the kite is 130 feet away from the child? All right, so the most important thing here is to be able to draw a picture. So the way that I'm interpreting this is we've got the child here at this dark point, and the kite is on a string, and the vertical or perpendicular distance from the ground up is 50 feet. I don't know the horizontal distance. It's in fact changing. And I don't know the length of the string. That's changing as well. So one relationship that I know automatically is no matter how much the string is let out, if the kite is flying, it says it's maintaining at a height of 50 feet, so it's going straight across. So it's always going to be a right triangle shape similar to this one. I don't mean similar like with the same angles, by the way. The angles are changing. But anyway, so the relationship between x and y is based on the Pythagorean theorem. We know that x squared plus 50 squared would be equal to y squared. And we're being asked about how fast must a child let out the string. Okay, so the string is the y side of the triangle. When they ask us about how fast, they're asking us about a rate of change with respect to time. So we're actually being asked about dy dt, right? The change in this length over time. We were also given information about dx dt, the rate of change of the horizontal distance. Is that right? Let's see. How fast must the child let out the string when the wind is carrying the kite horizontally away from the child at 26 feet per second. So we're being told that at this particular moment in time, or maybe constantly, dx dt is 26 feet per second. Okay, so again, dy dt is how fast the child is letting out the string, the change in the length of the string. Dx dt is the change in the horizontal distance from the child to the kite. We need a relationship not just between x and y, but we also are interested in dy dt and dx dt. So we need to find a relationship by taking the derivative with respect to t of both sides of this known relationship. So I'm going to take the derivative with respect to t of both sides, and we're going to get 2x plus the derivative, or actually, bad teacher, 2x, if this was the derivative of t squared, it would just be 2t, right? But it's not a t, rather, it's not an x we're differentiating with respect to. When these two variables are different, we need to also compensate for that. So I should have written times dx dt, plus the derivative of a constant, no matter what variable you're differentiating with respect to, is just going to be 0. And then over here, derivative of y with respect to t, so we're going to have to compensate again, kind of like the chain rule. So we're going to take the derivative of y squared, normally, 2y, but we're going to multiply by the derivative of the y, dy dt. Okay, so now we have this relationship that has all the variables in it that we're dealing with, right? The x, the y, the dx dt, and the dy dt. All right, so let's see what they're asking us to try to find. It says, how fast must the child let out the string, so find dy dt, when the kite is 130 feet away from the child. Now, if they wanted the kite to be horizontally 130 feet away from the child, in other words, if that 130 were x, they would say horizontal distance. But they didn't, so they're talking about the shortest distance between the child and the kite, which is the distance y. So this 130 is talking about y. All right. A child flies a kite at a height of 50 feet. The wind carrying the kite horizontally away from the child at 26 feet per second. Remember, we said that's dx dt. So we have dx dt, we have y, and we are looking for dy dt. But this equation requires that we also know x. So we can't plug in and solve for the one unknown dy dt until we know the other three unknowns as well. But luckily we know a relationship just between x and y. So let's go back to x squared plus 50 squared equals y squared. So if we still need an x to be able to plug into this equation, we can use this guy. We know that y is 130, so really x squared plus 50 squared equals 130 squared. And solving for x then, x squared is equal to 130 squared minus 50 squared. It's going to be 14,400, which is a perfect square, so that means that x is the square root of that, which is 120. All right, so now we have our x, our y, and our dx dt, and we can plug them all into this equation down here. So we're going to have 2 times x, where x was 120, we just found, times dx dt, which is 26, that was given to us, 26 feet per second, equals 2 times y, which y was given to us to be 130, times dy dt, the unknown that we're looking for. So that's going to be 240 times 26 equals 6240 equals 260 dy dt. And then we're going to divide that by 260 on both sides, and we get dy dt equals 24. So it would be 24 feet per second. Okay, make sure to let me know if you have any questions about any part of the problem. I'm going to give you a minute to let me know, and then what I'm planning to do next is, let me see if I can find the next one. The next one that I thought might be a challenge for you was number 5, so I was going to move on to number 5 if there are no questions. Okay, so I'm gonna, again, feel free to interrupt me, it's okay, because there is a bit of a time difference between when I speak and when you hear me. Okay, so number 5 that I was referring to is this one. Oops. It says a rectangular tank that is 108 cubic feet with a square base and an open top is to be constructed of a sheet of steel of a given thickness. Find the dimensions of the tank with minimum weight. Okay, so first of all, concept-wise, this is a minimization problem, right? Whenever you're asked to maximize or minimize, you need to have a function to do that. So we got to figure out what it is about this tank that's going to determine the weight. So first let me just draw a picture. This is a tank with a square base. It has no top on it. Right, so we can see in there. Okay, so here's our tank. And it's going to be made out of a sheet of steel that they're going to be folding together, I guess. And we don't know the thickness, it just says a given thickness, so that means it's the same thickness all the sheet. So what would determine the weight of this? Not the actual weight, but what characteristic would maximize or minimize the weight would be how much of this sheet we actually use, right? Which would equate to the surface area. So the function, in order to minimize the weight, we would have to minimize the surface area. So we're looking for a minimum surface area. Okay. Now, when I looked at the problem, the first thing I thought about was what they were giving me. They're giving me the volume, and you can tell it's volume because it's cubic units. So they're giving me the volume, and so I want to understand like what that's communicating to me. So I thought about what is the formula for the volume of this object. Well, since the base is a square, if I let each of the sides of the base have the length x and maybe the height be y, then the volume is going to be length times width times height. So it's going to be x squared times y. So what they're telling me is there's a relationship between x and y. Specifically, 108, the volume, equals x squared times y. All right, so that is a good fact to kind of keep in our toolbox, and then most likely we will have to use that fact to come up with a function for the surface area. So now let's try and write an equation that represents the surface area. Remember, surface area is just the sum of the areas of all the sides. In this case, the base is going to be x by x, which is x squared, plus each of the sides is going to be x times y, but there are 4 sides, so 4xy. So using the same x and y that I did over here in the dimensions in my diagram and in my volume expression, well, volume equation, I have the surface area equals x squared plus 4xy, but in order to maximize or minimize, I need a function of one variable, and notice that we have 2 variables here, an x and a y. So what I'd like to do is to replace the y with what it's equal to in terms of x. Y equals what? So coming back over here, that's always where this extra piece of information they give you will come in handy. If I solve for y, we see that y is actually equal to 108 divided by x squared. So if I plug that in for y in the surface area equation, I'm now going to have something that's strictly a function of x. Excuse me. The surface area is a function of x because I'll write x squared plus, and then we have 4x times 108 over x squared. So that's going to be 4 times 108, which is 432. And then one of the x's cancels, so it's going to be over x. So this is the function that you need to minimize. Okay, how do you minimize a function? Can anyone type into the chat bar how you minimize a function, how you find the minimum value or maximum value for that matter? What do you need to find first? Nobody? So do you need to find the first derivative, perhaps? And what do you need to do with the first derivative? That's right, set the first derivative equal to 0 and solve for x. So let's go ahead and find the first derivative here. I'm gonna, let's see, do I have room down here? I think I do. All right, so we're gonna move down here. So if s of x is x squared plus 432 over x, by the way, that's not a nice form for taking the derivative. You can, but you'll have to use the quotient rule for 432 over x. So instead, I prefer to think of this function s of x as x squared plus 432 times x to the negative 1, and that way I can use the power rule instead. So the first derivative is going to be 2x, and then using the power rule, we bring the negative 1 out front, so we have minus 432x to the negative 2. And I'm going to write that with a positive exponent because that is easier to work with algebraically. So this is my first derivative as I would like to work with it. And as you pointed out, we're going to set that equal to 0 to find where the derivative is 0. We also know the derivative is going to be undefined at x equals 0. So that is a partition value, but not a critical value because, let's see, the original function is also undefined at that value. So that can't be our max or min anyway. But it is a point where the sign could change on the first derivative, so keep that in mind. All right, so we have, let's move the 432 over x squared to the other side, so it'll become positive. Multiply both sides by x squared, so we have 432 equals 2x cubed. Oh, look at that. We can solve this by factoring. So we're going to have 0 equals 2x cubed minus 432. And dividing by 2 then, 0 equals x cubed minus, does 2 go into there? Let's, of course it does. 432 divided by 2. 216. Is 216 a perfect cube? Because then we have a difference of cubes, so that would factor nicely. Yes, it's 6 cubed. So we have 0 equals x cubed minus 6 cubed. And I don't know if you recall, but to factor a difference of cubes, a cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. Okay, and a cubed plus b cubed, by the way, factors into a plus b times a squared minus ab plus b squared. Okay, so we're doing a difference of cubes, so that means that we are going to have 0 equals x minus 6 times x squared plus 6x plus 36. Now, it's always the case that this guy over here can't be factored, at least over the integers. I think more than likely any roots of this are going to be imaginary numbers. Let me see. We're going to have x. Well, what I'm saying is that we can set x minus 6 equal to 0, but we can also set x squared plus 6x plus 36 equal to 0. If x minus 6 equals 0, then x would be 6. And then over here we would have, this is a 6 by the way, not a b, and this is a 6. All right, so x would be negative 6 plus or minus the square root of b squared, which is 36, minus 4 times 1 times 36. So you see how in the discriminant here under the radical we're going to get a negative. So this is not going to give us a real solution. So the only real number solution is going to be x equals 6. All right. So now let's make a sign chart for the first derivative, and let's see if we have in fact a minimum value here. So since we're talking about a context where x is a length, the smallest length that x could be would be 0, but in fact this function is undefined at 0. So I'm just gonna remind myself of that. not going to be concerned about negative values of x, so I'm going to squiggle that out there. I'm just going to put the 6 that we are concerned about for the x values. That's a critical value. It makes the derivative equal 0. And then I'm going to check values on these intervals and see if we have a minimum. So any value on this interval will work, like 1 or 10. And if you plug it into s prime of 1, we don't really care what the value is, just whether it's positive or negative, right? So 2 times 1 minus 432 over 1 squared is definitely going to be less than 0. It's going to be negative. Okay, and then s prime of 10, we're going to have 2 times 10 minus 432 over 10 squared, or 100. So that's going to be 20 minus about 4, which is going to be greater than 0. So that's positive. So when the first derivative is negative, that means that the original function s is actually decreasing. And then when the first derivative is positive, the original function s is increasing. Okay. All right, so definitely we have a minimum when x is 6. So let's go back up and see what we were asked to find. Find the dimensions of the tank with minimum weight. Okay, so we have a minimum surface area which causes a minimum weight when x is 6. But we need all 3 of the dimensions. So we have 6 and we have 6, but we need to figure out y. But remember, y is equal to 108 over x squared. So y is equal to 108 over 36, 6 squared, which is what, 3? So the dimensions are 6, 6, and 3. Okay, so any questions about that exercise? The important thing to grasp there is that in these problems where they're asking you to apply the idea of maximizing or minimizing, you often have to construct your own function. And there's always this extra piece of information that enables you to make sure the function only has one variable. Like in this case, we had the volume to help us do that. All right, so if you, again, have any questions that you in particular would like me to work, you can let me know. Otherwise, the next one that I wanted to look at was number 10. Okay, so here's number 10. It says find a linearization at a suitably chosen integer near a, at which the given function and its derivative are easy to evaluate. And the function is f of x equals 2x squared plus 5x minus 3. Okay, so a linearization is a line, a tangent line to the curve at a particular point, and anywhere near that point it gives a good approximation of the function. And so this is nice for estimating, and you want the arithmetic to be easy. So for example here, if we wanted to use a linearization to evaluate this function at negative 0.9, estimate it actually at negative 0.9, we would want to use a value really close to negative 0.9, like negative 1, which is a nice integer value close to negative 0.9. So when they ask you what x value you're setting the linearization at, all they're asking you is what's a nice integer close to negative 0.9, so we're going to use -1. The other thing I want to make sure you know is the formula for linearization. So the formula looks kind of scary, but once you know where it comes from, it's not so bad to remember. So the linearization function L of x equals f of a plus f prime of a times x minus a. Okay, this will give you a tangent line to the curve at a. In this case, we're going to let a be -1. But I want to show you that this is really just the point slope form of a line. You remember when you were learning how to write equations of lines given a point and a slope, we learned y minus y1 equals m times x minus x1. Well, if you move that y1 over to the other side, you have y equals y1 plus m times x minus x1. And in our formula matches up with that, because look, y means f of x, right? So this is our y, our function. And then x1 is just a particular x value. The x value we're working with is a. This is x that is just the same thing in this formula. The slope is the derivative. Remember, derivative is slope, so it's the derivative at a. And then this is the y value at a from the original function. Okay, so this is really just the point slope form of the line, but we're looking at the point a f of a, and we're using the slope that is the derivative at a. Okay, so but let's go ahead and in order to actually do this problem, you need to write down the formula, and then we're going to need f of a, and we're going to need f prime of a. So let's go ahead and find f of a first. So that's -1 minus 3. So that's going to be 2 minus 5 minus 3 is going to be -6. Okay, and then we also need to find f prime of x and plug -1 into that. So the derivative of 2x squared plus 5x minus 3 is just 4x plus 5. So if we plug -1 into that, we have -4 plus 5, which is just 1. Okay, so now we have what we need to plug in. So L of x is going to be f of a, which was f of -1, which was -6, plus f prime of a is the derivative at -1, so that's going to be 1, times x minus a, so x minus a -1 is x plus 1. So simplifying a bit, L of x is going to be -16 plus x plus 1, so L of x is going to be x minus 5. Okay, so what they're looking for here in this problem is just x minus 5. So this line is very close to the function f near the point -1, and I just want to bring up Desmos.com and graph this for you real quick so you can see. Okay, so here's the function 2x squared plus 5x minus 3. We're going to graph along with that the linearization function, which we found, which was x minus 5. And so first of all, see that this is the graph of the function, the tangent line to the graph at -1. So it's going to be really, really close to any y values on the red graph are going to be very, very similar to the y values on the blue graph. So for example, if I wanted to plot the point -0.9, remember the x value we started with was -0.9, and plug that into f, the actual function, then we would get -0.9 comma -5.88 on the red graph. But if we plug it into the linearization, -0.9, plug in the y value for -0.9 on the linearization, we're just subtracting 5, right? X minus 5, so it's going to be -5.9 there. So that color's kind of pale there. So anyway, it would be a lot easier to plug -0.9 into x minus 5 and say -5.9. Very quickly we would get a value, as opposed to plugging it into 2x squared plus 5x minus 3 and doing all that to get -5.88. So if you only need it to one decimal place, then you're good to go on that. And any values close to -1 are it's gonna be a similar situation. Okay, so that's the linearization. Again, if you have any questions so far or a particular one on the review that you want to look at, please let me know. Otherwise, we're going to move on now to item number 12. Okay, so here's item number 12. It's kind of a classic problem. You see this a lot in different calculus books and standardized tests. A 10-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 8 feet from the house, the base is moving away at a rate of 12 feet per second. What is the rate of change of the height of the top of the ladder? That's part A. And part B, at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing then? And part C, at what rate is the angle between the ladder and the ground changing then? Okay, so this is a related rates problem as well. And these always give people trouble. So let's take a look. So they have been kind enough to provide us with a diagram this time. I'm going to zoom in a little bit on that diagram and fill in what we know. Okay, so here's my diagram. And the first thing that they told us was that the ladder was 10 feet. So they've already labeled that, but let me just label that on there. All right, I wonder if I have a white. No, I don't. Okay, the next thing that they tell us is that by the time the base is 8 feet away from the house, so this is your house over here. Leaning against the house. By the time the base is 8 feet away from the house, so at the moment when this distance here is 8 feet, or in other words, when x is equal to 8 feet, the base is moving away at the rate of 12 feet per second. So what they're describing there when they say 12 feet per second is a rate, a velocity, if you want to think of it that way, right? And it's the rate at which this distance is changing, because it's not always 8 feet. At one moment it's 8 feet, but the next moment it's going to be 10 feet and so on. So what they're talking about is the change in x. So we can label this dx dt. They're telling us dx dt is 12 feet per second. Okay. Now, we also have a variable y, which is the height of the ladder, the top of the ladder, or another way of describing it is the distance from the ground to where the ladder meets the building. That's y, but that's changing too, right? And the rate of change of that guy would be called dy dt. So these are all 4 variables: x, y, dx dt, and dy dt are all variables that we're interested in. Now you might notice that once again, just like in the last related rates problem, we have a right triangle. And we are concerned about the lengths of the sides of that right triangle as time goes on. So the relationship, though, even as the ladder slides down the wall, is still going to be a right triangle. So our sides will still be x squared plus y squared equals 10 squared according to the Pythagorean theorem. That's a relationship that will hold steady. Now, of course, that relationship relates x and y, but it doesn't relate all 4 of the variables that we want. We also are interested in the rates of change, dx dt and dy dt. So we can use that to get another relationship by taking the derivative with respect to t of both sides of that equation. So we're going to take d dt of x squared plus y squared and d dt of 10 squared, or 100. Now when you take the derivative with respect to t of something with an x, you have to compensate for the fact that that wasn't a t. So it's going to be 2x dx dt by the chain rule plus derivative of y squared is 2y dy dt. And then on the right, derivative of 100 is just 0. So we get the same relationship we got before, if you recall, in the other problem. And that's a relationship you're going to get whenever you have a right triangle. And now we want to plug in everything we know and find what we're looking for. Okay, so what are we looking for? In part A, it says, what's the rate of change of the height of the top of the tower? Right, so in part A, we're actually looking for dy dt. That's the rate of change they're describing. So we need to know all the other variables in the equation. We know x is 8 at that moment. We know dx dt is 12 at that moment. We're looking for dy dt, but we also need y. So once again, we can use this x squared plus y squared equals 10 squared to get the y that we're looking for. So let's do that. So if x squared plus y squared equals 100, and we know x is 8, that means 64 plus y squared equals 100. That means y squared is 100 minus 64 is 36, so y would be 6. And it's distance, so I'm going to leave it as the positive version. So now we have y. So let's plug everything in. So we have 2 times 8 for x, dx dt is 12, plus 2 times y is 6, and the dy dt that we're looking for stays a variable. So then we're going to have 16 times 12 is 192 equals 2 times 6 is, plus, not equals, plus 12 times dy dt equals 0. Subtracting 192 and dividing by 12, we get dy dt equals negative 192 over 12, which is going to be negative 16. Now you might be wondering why we got a negative on a rate. This is still feet per second, but remember the ladder is sliding downwards. So that means that the distance is actually shrinking between the ground and the top of the ladder. So that's why the velocity is a negative. All right, so it's a directed velocity. So for part A, the answer is negative 16 feet per second. Now the next part of the question is to find the rate at which the area is changing, the area of the right triangle. So let's talk about the area of the right triangle. Okay, so how do you find the area of a triangle? You find the area of a triangle by taking 1/2 the base times the height. So I'm going to come down here and redraw my diagram. Okay, the base is x, the height is y. So the area of this triangle is 1/2 times x times y. We want to know the rate at which this area is changing. So we want information about dA dt. So in order to get dA dt, we're going to have to take the derivative of both sides of this equation with respect to t. Oh. Now, this can throw people off because, okay, on the left we just have dA dt, that's no problem. But on the right, notice that you have a product, right? You have 1/2 x times y. So you're going to have to use the product rule to take the derivative. So we're going to have the first function is 1/2 x. Times the derivative of y is dy dt plus the second function, which is y, times the derivative of the first, which is 1/2 dx dt. So again, we just applied the product rule, which you might not think of because it's got different variables in it that might throw you off. But whenever you have something with a variable times something with a variable, that's a product rule to take the derivative. Okay, so now to find dA dt, we need all these different pieces of information. We need the x, we need the dy dt, the y, and the dx dt. But we have all of those because we found them earlier. So remember, let's see, 1/2 of x was 8. dy dt we found was negative 16. For y, we had found that that was 6. And then dx dt was 12. Okay, so let's multiply this all together and see what we get. Gonna get 4 times negative 16 is negative 64, plus 3 times 12 is 36. Negative 64 plus 36 is going to be negative 28 square feet. Remember, this is a rate of change of the area, which is being measured in square feet. So it's going to be square feet per second. Why is it negative 28? Because the area is getting smaller as the ladder gets closer to the ground. Whoops. Okay, so let's fill in the next answer here. Negative, what did I say? Negative 28 feet per second squared. Okay, and then there's one more part to this. It says the angle is changing at blank radians per second. So what angle are they talking about? Let's go look at the original diagram there. They have marked an angle theta here. Okay, so we want to find d theta dt, the rate of change of the angle theta. And the information that we have is all in terms of x and y, which are the sides of the right triangle. So what trig function would relate the side opposite theta to the side adjacent to theta? So opposite over adjacent would be your tangent function, right? So in this case, the tangent of theta would be y over x. So that would give you a relationship between theta, y, and x. All right, so let's write that down. Oops, did it again. I go too far down or up? Okay, so I'm going to make myself a little room over here. I'm going to draw my picture again. Here's theta, here's y, and here's x. So we just talked about how the tangent of theta is going to be y over x. So that gives us a relationship between the x, the y, and the theta, but we are trying to find the rate at which theta is changing. So we are being asked to find d theta dt, the rate of change of the angle over time. So the only way to do that is to take the derivative of both sides of the relationship that we just constructed. So we're going to take d dt of tangent of theta and d dt of y over x. Okay, so what's the derivative of the tangent function? I'm sure you've been doing it so much that you probably have that memorized, so hopefully you know that that is going to be secant squared theta, but remember, that's if you're taking the derivative with respect to theta. We're taking the derivative with respect to t, so we need to say times d theta dt equals, and then over here, how do you take the derivative of a quotient? You have to use the quotient rule. So we're going to take the derivative of y over x with respect to t. So we're going to have the bottom function times the derivative of the top, dy dt, minus the top function, which is y, times the derivative of the bottom, which is dx dt, all over the bottom squared. Okay, now before we go on any further, rather than try and figure out what theta is when x is this certain value and y is a certain value, in order to figure out secant squared of theta, I'm just going to use my little triangle here. So I'm going to, remember, secant is just a ratio of the sides. So we have the sides, so let's see. This is 10, by the way, in case it matters. Let's see if it does. So secant is the reciprocal of the cosine, and I'm more comfortable with cosine. So cosine of theta is adjacent over the hypotenuse. Adjacent over hypotenuse, which in this case would be x over 10. So that means that the secant of theta would be the reciprocal of that 10 over x. And so secant squared of theta would actually be 100 over x squared. So in my formula, rather than having secant squared of theta, I'm going to change that to 100 over x squared d theta dt equals x dy dt minus y dx dt over x squared. This is the cleanest way to do this. So now we just have to plug in things that we know, right? We know x, we know y, we know dy dt, and we know dx dt, and solve for the unknown, which is d theta dt. So plugging in, you might even notice that there's a x squared in the denominator on both sides, so really you could clear that. That'll make it even simpler. Here we go. All right, so we have 100 d theta dt equals x dy dt minus y dx dt Oh, with no denominator, so we're good there. Okay. So now let's plug in the values that we know. So that's 100 times d theta dt equals x, we were given was 8, dy dt, we figured out was negative 16, y, we figured out was 6, and dx dt was given to us as 12. So that means 100 d theta dt equals, that's going to add up to negative 200. So d theta dt, if you divide both sides by 100, will be negative 2, and that's going to be in radians per second. So let's go ahead and put that in there, negative 2 radians per second. Okay, well, it's 5 o'clock. It's getting kind of late. So I'm going to go ahead and stop there. But you can access a printout of the quizzes here, and solutions. Even if you scroll down to the bottom, we have all the answers as well. So if you want to, you can practice these problems before or after taking the quiz, but definitely before you take test 3. If you have any questions about anything in the meantime, just go ahead and email me. And thank you guys for coming out today. If you could give it a thumbs up before you leave if it was helpful to you. That helps other students to find the video, which will be posted in YouTube. Thank you very much. Bye-bye.